Hey everyone, welcome back to Calculus 1. This will be part B of lecture 4. And in this section, we're going to continue with our discussion of continuity. So we want to jump into a theorem next. So this theorem says, let f be a function and let c and L be real numbers. The limit of f as x approaches c is L if and only if the left-hand limit and the right-hand limit equal L. Okay, so we may have mentioned this before, but this is a theorem now that we have the idea of a left-hand limit and a right-hand limit. We can say that the overall limit exists only when the two one-sided limits agree. So we can now say that a limit exists only when both one-sided limits agree. So obviously they must exist and they must agree. The one-sided limits also allow us to extend our definition of continuity to include the endpoints of intervals, right? So if you recall our definition from the previous section, we said that we only discussed continuity on an open interval. So on a closed interval, what you'd have to do is extend to those endpoints, right? And so now that we have left and right hand limits, we can extend our definition to include closed intervals. And so we do that by saying that a function f is continuous on the closed interval, AB, if it is continuous on the open interval, right? So naturally, every point inside the open interval has to be continuous. And now the endpoints have to be continuous from the left and from the right, right? So the limit as x approaches a from the right of f of x is equal to f of a, and the limit as x approaches b from the left of f of x is equal to f of b, right? So we have to be able to approach a from the right and have it equal f of a, and we need to be able to approach b from the left and have it be equal to f of b. Okay, so we can now extend our definition to a closed interval basically just by checking the endpoints, right? So all these points in here, the function's continuous at, and then we just need to do a right-hand limit and a left-hand limit check on those endpoints. And if those also exist and they meet the definition, if those limits exist and are equal to f of a and f of b, then we have continuity on the closed interval. All right, very good. So let's take a look at an example. The function, we saw this in the previous example, the function f of x equals square root of 4 minus x squared. This is a semicircle in quadrants 1 and 2. This function has a domain of -2, 2. At all points in the open interval, the continuity is already established. You just look at the graph, you can see that that works out. What we can do next is we can check the limits at the endpoints, right? So the limit as x approaches 2 from the left, this one, is equal to 0, right? So we can plainly see that that limit is heading to 0, and that's equal to actually the function evaluated at 2, right? So if I plug a 2 in here, I get square root of 0. And similarly for this one, if I approach from the right, I can see where this function is headed, and it is headed to 0. And further, if I plug -2 into this, I get 4 minus -2 squared, which is equal to 0. Okay, and so we can see, therefore, that these two conditions are satisfied, and we have continuity on the open interval. And so that means f is continuous on its entire domain. Perfect. Nice thing to be able to say. All right, very good. Now, what we'll do next is kind of standard boilerplate for calculus. We establish an idea and a definition, we maybe crank out a theorem, and then we start extending it to all kinds of combinations of functions. And so the next theorem does this. So if b is a real number and f and g are continuous at some value, x equals c, some real number c, then the product of a constant and the function is continuous. F and g added or subtracted together are continuous. F and G multiplied together are continuous. And the ratio F over G is also continuous, right, at that point C, right? So basically, if you have two functions that are continuous, you can add them, multiply them, divide them, whatever, and you get a continuous function as a result. Okay, very good. And so there's a whole range, we've seen examples already, but there's a whole range of functions that are continuous throughout their domain. And we're going to kind of explore some of those now. And so the following functions are continuous at every point in their domains. So the first big class is polynomials. And we've seen examples of polynomials are just convenient functions to use in general. And when it comes to calculus, they are the creme de la creme of nice functions to work with. They're smooth, they're continuous. Later we'll see they're differentiable everywhere, etc. And so all polynomials of this form are continuous on all real numbers, right? So this is just the standard polynomial notation, right? So 2x squared plus 3x plus 4, continuous everywhere, right? So polynomials are the first big class of functions that are always continuous. The next big class would be rational functions. Now, rational functions, remember, are ratios of polynomials. So you got a polynomial in the numerator and a polynomial in the denominator. And it turns out that these guys are also continuous everywhere. And they're continuous everywhere so long as the denominator is not equal to 0, right? So when you have a 0 down here, then you are going to get a hole. But outside of that, they're continuous on the entire real line, and specifically they're continuous on their domains, right? That's really the key here, on their domains. Rational functions, another one, the square root of x, continuous everywhere on its domain, right? There's no part of its domain that is problematic, okay? Trig functions, we've all seen sine, kind of goes up and down like this. Everywhere continuous. There are no gaps or holes in the sine functions. Cosine, tangent, secant, cosecant, etc. All the trig functions are continuous everywhere on their domain. Okay, so very nice. And then exponential and logarithmic functions. So things like the f of x equals a to the x power, continuous on its entire domain. G of x equal to e to the x, continuous everywhere on its domain. And the natural log of x would be another example. And then any combination of these things as well, continuous on its entire domain. Okay. And so here's, let's take a look at an example, see how these 5 classes can all be kind of combined together, and they frequently are. Let's take a look at some examples of that. So is f of x equal to x plus e to the x everywhere continuous? Well, yeah, so I kind of color-coded this. X, I'm going to call g of x, and e to the x, I'm going to call h of x. G of x equals x, that's just a polynomial. So we got a polynomial there. And then h of x equal to e to the x, that's just an exponential function, right? So I got an exponential function there. So this is continuous on its whole domain. That one is also. And so yes, this function is everywhere continuous, no holes, no gaps, no problems. What about this guy? Is f of x equal to x squared plus 1 over cosine of x everywhere continuous? Well, yes, this is the ratio of a polynomial and a trig function, right? So the polynomial is continuous for all real numbers. The cosine function is continuous also for all real numbers. Now, this guy can technically equal 0, so the domain of this function will be constrained a bit, but it is everywhere continuous on its domain. Right? There's no part of the domain of f where we don't have continuity. There's no gaps or no steps. There's no weird things happening. You do have issues, but those issues occur outside the domain of the function. Very good. Okay, a theorem. So this theorem deals with how do we think about the continuity of composite functions. So compositions of functions. So if g is continuous at x equals c, and f is continuous at g of c, then f composed of g, which there's different ways to notate it. You can denote it like this or like this, but f composed of g is continuous at c as well, right? So as long as g is continuous at c, and f is continuous at whatever value you get when you plug c into g, then the composition of the two is continuous at c as well. Right? And let's see an example of that. So think about this function, h of x equals the sine of 3x. Right? So notice that f of x equals sine of x and g of x equals 3x. And just kind of using the sort of the parlance of the previous theorem, right? So notice this, and so that implies that h of x is equal to f composed of g, right? So sine of 3x, right, naturally. And so notice also that f and g are both everywhere continuous, right? And therefore the composition is as well, right? So not a problem, right? Anywhere you can plug in an x, you can certainly plug in a 3x, not a problem. Here's another way to think about continuity, another kind of example. On what intervals is f of x equal to tangent of x continuous? Okay. And so this isn't a question about its domain. It's a question of like on what intervals of the real number line, right? So we know from our trig in our algebra classes that tangent of x is asymptotic at pi over 2 and negative pi over 2. And in general, it's going to be asymptotic at pi over 2 plus any multiple of pi, right? And so we've seen the graph for tangent before. Kind of looks like this, right? You've got, here's x equals 0, and you've got x equals negative pi over 2 and x equals pi over 2. And the function kind of exists between these asymptotes, right? You know, kind of, it's one of the weirdest functions you ever plot, right? And it looks a bit like that, right? So it's got this sort of asymptotic behavior that's periodic. And so those occur at pi over 2 plus n pi. So at these points, the tangent function, the graph of that function, has a non-removable discontinuity, right? Right here, these are all non-removable discontinuities. But at all other points, tangent is continuous. The tangent function is continuous on all of these other intervals, across all these intervals, right? It's just these values here, pi over 2 plus m pi, where we have issues. Very good. All right. Now this next theorem is kind of a famous one, and it's famous. It's very useful. It comes up later in calculus a lot. It comes up in strange places, in proofs, in analysis, and so we go through it, but it's super intuitive. I think anybody, it's not hard to see why this is true. The theorem says if f is continuous on a closed interval AB, right? So I've got a function that's continuous on a closed interval, which basically means there's no breaks or gaps in the function. And k is any number between f evaluated at the low point of the interval and f evaluated at the high point of the interval. Then there's at least one number c inside this, so somewhere between a and b there's a c, such that f of c is equal to this